Well, it's hard to believe the semester is just about over. So anyway, this is the final exam review slides with that. So a lot of these, so the exam is going to be just free answer parts, so no multiple choice. With that. So we're going to have these different sort of questions written. So if you want to, please look at the final exam review topics for that. For a definitive list, but this is going to be pretty much the types of questions that you'll see. They're going to be very similar to the previous exam, so take a look at those, and you'll get a flavor for what we need to do for this one. So the exam isn't hard; it's just long. But anyway, so we'll go ahead and go right away. So one of the things we're doing right is hybridization. All right, so we're looking for SP, or you can think of SP1, SP2, SP3. Stuff like that. So, what are we looking for hybridization? Well, we're looking at, is it the bond sets, right, plus lone pair sets, right? So when you add that together, right, that'll get the number. That's the amount of letters that we're going to need, right? So you start with S and then you just add P's until you get to that number, right? So this one here, right? So for this carbon here, right, there's 1 and 2, right? So each for the bond sets we consider single, double, and triple bonds all equivalent, right? So here we have two bond sets, right? And right, so with no lone pairs, right? So it's so the final answer is 2, right? So that means we need letters S and P, right? So it's S, and then to make the second letter we need just add 1 P. So it's an SP orbital, or you can think of it as SP1, right? So for this one here, right, we have 2 bond sets, right, plus 2 lone pairs, right? So it's 4, right? So that means we're going to have 4 letters. So you go S, P, 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 right? Which is SP3 or SP cubed, right? So there we go. So that's what you're looking for. So just don't forget that single, double, and triple bonds in this case, they all count the same. So there we go. Okay, next up, formal charge. Okay, so with formal charge, what you're looking for is valence electrons. This is on periodic table, right? So periodic table. How much would it normally have on the periodic table? Minus electrons now. Right? Okay, so when you have this, right, so you have a bond, right? So remember, each bond is worth 2 electrons, right? Right, so what are we going to do? We're going to slice those bonds in half, and each atom gets 1 of those electrons, right? So the oxygen atom goes like this. 1 electron, 2 electron, 3 single, right? So each one of these bonds contributes 1 electron, and you have this lone pair down here, right? So this just stays right on the oxygen. Right? So how many electrons would oxygen normally have? Well, you just count over, right? 1, 2, 3, 4, 5, 6. That's what it normally have on the periodic table. Right? So 1, 2, 3, 4, 5, 6. Right? So like that. So now it has, so that's what it has now. Right? Minus what it has now, which is 1, 2, 3, 4, 5. Right? So the formal charge is plus 1. That's about the easiest way to do this. Okay, so plus 1. So it's, Next up, resonance structures. Okay, so you can sort of think of resonance structures as wanting to get carbons that only have 4 bonds. So that's one way to think about this. Okay, and you can actually, it may be a little easier to go ahead and just draw out the rest of these hydrogens, right? So it makes the formal charges a little bit easier to see. Okay, but in order for it to participate, an atom to participate within the resonance structure, it has to satisfy one of 3 things. Either it needs a charge, it needs a set of lone pairs, or it needs to be part of a double bond or a triple bond as needed. Right, so it needs pi electrons. Okay, so this carbon here. So all of these are either part of a double bond or have a charge. This one here only has a single bond, doesn't have any of those. So this carbon atom here cannot participate. Okay, but the rest of the 5 of them can. Okay? And so what's going on here is, right, so this carbon atom only has 3 bonds, right? It wants 4, so what it does is it actually so what this carbon atom does is it says, okay, I'll give you this set of this bond here. This carbon doesn't matter, it doesn't care because it already has 4. It has 4 bonds now, it has 4 bonds after it moves, right? And so what ends up happening is you get this situation, right? Right, now the double bond is moved here, right? So this carbon here has its 4, this has its 4, right? That has its 4. Now this carbon here, after this double bond is shifted over here, now it only has 3, so the plus charge ends up there. Okay. Now it's searching for a 4th bond, and so this double bond can move over. Okay, and so now you can get that double bond gets shifted over here, right? And now this one is the only one that has three atoms attached to it, or 3 bonds. So this has a plus charge, right? And we can't go further around, right? Because it needs to stop here because there's no, this one can't participate in the resonance structure, right? So there's 3 resonance structures. But notice how the charge starts here, skips this one and goes there, skips this atom and goes there. So you'll see this a lot. Where you get this skipping effect around here. These are the resonance structures. Okay, so draw all possible ones. Okay, so naming structures, right? So when you have a structure like this, right? So for alkanes, never a bad idea to go ahead and just put dots for the carbons, right? Just a little bit easier to see. Okay. Now, one thing, right? So you can always start with the horizontal chain, right? So first step is always getting the longest chain, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But don't forget to go down the side chains as well, right? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's really close to do that. Is to go this way. So you have to keep counting. But in this case, it just so happens to be the horizontal chain. So in this case, it's 9, so C9, which is it's all single bonds, so it ends up being no name. Okay, but we also have, right, this here, here, and here, these side chains. Now those 9 carbons there, those are taken up by this no name here. It's just the ones off of the double bonds where it has, right? So you have a methyl group here, right? You have 2 methyls, methyl, methyl, and then you have that ethyl group there. It's a 2 carbon piece, right? So it's methyl. Okay, so there's no priority groups or whatever, but that's what we're gonna have to do for both sides, right? So if we're gonna take it from take one from this side, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this methyl group's at 3, this methyl group's at 5, this methyl group's at 4, right? The other option would be to say, sorry, on this side would be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this methyl group's at 7, this one's again at 5, this one's at 6, right? So you add them up, right? So that's 7, so this would be 12, this would be 11, this would be 18, right? So this adds up to the smaller number, so there we go. Okay, so what comes first? Methyl or ethyl? Ethyl comes first, right? So it becomes 4-ethyl, 3,5-dimethyl, no name, right? So don't forget, if there's a di here, I need 2 numbers there, even if it's the same, even if it's 5,5-dimethyl or 3,3-dimethyl. I still need 2 numbers here if I've got a di. If there's a tri, I need 3 numbers, right? And also don't forget, the di doesn't matter as far as alphabetical goes, right? It's just methyl versus ethyl, right? So ethyl comes before methyl. The di does not matter. It's ethyl comes before methyl. Okay. Cool. Sorry, I forgot to move that along. So there we go. 4-ethyl, 3,5-dimethyl, no name. Okay. You can also work backwards, right? So if you want to say, oh, I've got a carbon chain that's 9 long, right? I have 2 methyl groups, right? One at 3, one at 5, right? And I have an ethyl group hanging off of carbon 4. There you go. Right? Hanging off of carbon 4. These guys here hanging off of 3 and 5. So there you go. You can always go back and recheck. Okay, so for acid and base, this is pretty straightforward. Okay, so what do acids do? Right? So they give H+, right? What do bases do? Right? They take H+. Okay, that's the easiest thing. So what's the most acidic hydrogen on here? It's actually this one right here. Okay, and so this set of lone pairs is going to come make a bond there, right? Because remember, this is electronegative, right? So this is that oxygen is more electronegative than oxygen, so right, so it's going to be partial negative, partial positive. So these electrons are going to be attached here, so it's going to take these 2 electrons to make a bond with that hydrogen. That's going to mean these 2 electrons here, because hydrogen can only have one bond, right, are going to be pushed up onto that oxygen, right, because hydrogen doesn't need them, right? So your 2 products are going to be this plus HOH. There you go. So this is the, so like that. So notice how there's a negative charge here. So overall, there's a -1 charge on this side. There needs to be an overall negative -1 charge on this side, which we have. So like that. So there we go. I don't have that up there, but that's the answer. Okay. Okay. I always like this. Okay. So you're going to need to circle and name the functional groups, right? So this particular one is this is the active ingredient Flovent, which is used for asthma. Notice the 4 rings here, the 6, 6, 6, 5. This is a classic steroid structure, stuff like that. And so there's a whole bunch of functional groups on here, so we're going to circle and name them. Okay. So here we go. So we have C double bond O, right? So you have to be really careful with C double bond. You have to see what's on either side of it, right? So there's carbons on either side of it, so that makes a ketone. Okay. If there's other things on either side of it, we'll have to be careful with that, right? So there's a double bond here and a double bond here. This is not a benzene ring, okay? Because benzenes are double single, double single, double single going around. Okay, so these are alkenes. Alkene, alkene. Oops. Spelled right. Okay. Notice this fluorine here and this fluorine here. These 2. Right, those are both halides. Halides, right? Spell. You can also call them fluorides, fluorines, or fluorides, or whatever. That's fine. So like that. So, right. So we're moving along, right? So there's just an OH, right? Just hanging off a regular carbon, right? So that makes this an alcohol. Okay, so we're moving along. Okay. So here we go. There's this one here. Notice there's a C double bond O here. Okay, but there's an oxygen with a carbon. Oxygen carbon on this side and the carbon on this side. So there's oxygen and then the carbon on this side. That makes a carbon on this side. That makes this group here an ester. Okay. This one here, notice the C double bond O here, right? Now we have a sulfur carbon, right? Carbon on one side, sulfur carbon on the other, right? So this is the sulfur version of an ester. So it's a thioester. Okay. So thio means sulfur. Refers to sulfur, right? So it's a sulfur version of an ester. So it's a thioester, just like a thiol is a sulfur version of an alcohol, something like that. So the thioester is the sulfur version of an ester, right? Okay, and then this guy here, right? Another halide or fluoride if you want to. So there you go. I don't think we missed any. Yep. There we go. So do your best on circling. Right? Usually get 1 point for circling, 1 point for naming it correctly. So that's flowing. Okay, so naming cyclic compounds. Okay, so 2 things you're going to need to know, right? So with that, well, 1, go ahead, just put in the dots, right? So it'll be easier to see the carbons. Right? Okay, now the main chain, it's either going to be ring or straight chain. It's not going to be both. It's not going to be a straight chain that goes into the ring. It's either going to be ring or straight chain. They're separate. Okay, so in this case here, right, we have this 6-membered ring here, right? The longest straight chain is actually this one here, 1, 2, 3. right? So this is the longest part, right? So that's C6, right? Which would normally be hexane, right? But since it's a ring, it becomes cyclohexane, right? And then we have that group there, right? So it's 1, 2, 3 long, right? So it's propyl. And then we have these two methyl groups, right? Separate methyl groups. It's not an ethyl group. It's two separate methyl groups. They just so happen to be hanging off of the same carbon, right? So what we'll do is we'll say, okay, we're going to say, what if wherever there's something attached to the ring, right, we're going to say that that's carbon 1, right? So if we're going to say this is carbon 1, you go towards the nearest neighbor, so it goes 1, 2, 3, 4, 5, 6, right? So that would make this one 1. These attached both at 2, right? But instead, if we went and we said, okay, what if this is number 1, then we'd go towards the nearest neighbor. That would make this 2, 3, 4, 5, 6. Okay, so that would make this 2, 1, 1. You add them up, right? So this is 5, this is 4. The smallest number set's this one, right? So the name is going to be, right, which comes first, methyl or propyl? Methyl does. So it'd be 1,1-dimethyl, right? 2-propyl, cyclohexane. Okay. Not too bad, right? We have a cyclohexane. Right? At carbon 1, we're going to just say, hey, that's carbon 1 here. We have 2 methyl groups, and then carbon 2, right? We have a propyl group hanging off. Not too bad. Okay, so the other one here is again, go ahead, put in your dots. It never hurts. Especially when you're starting out. Okay? So we have this 5-membered ring here, right? Longest straight chain is this one here. It's a 3, right? And it's a 1 or a 1. So it's going to be this one here. So right? So this is going to be C5, right? Which would normally be pentane. But because it's a ring, we're going to say cyclopentane. Okay? And again, we have that methyl, this methyl. Now this is a propyl, right? But remember it's 1 because it's 3 long. But since it's attached to carbon 2, we call that a 2-propyl group. Okay, this one was attached to carbon 1, right? So it's just a regular propyl. We can call it 1-propyl. This one's attached to carbon 2, so this is considered a 2-propyl group. Okay, so we're going to say each one of these is going to be carbon 1, and we're going to see what the numbering looks like. Okay, so if we're going to say this one's carbon 1, nearest neighbor's here, so it's 1, 2, 3, 4, 5, right? So it'd be 1, 2, 4, right? Now if we're going to say this is carbon 1, so 1, nearest neighbor's here, so 2, 3, 4, 5, right? So it becomes 2, 1, and then around 4, right? And then what if we said this was carbon 1? So 1, and then here it doesn't really matter which way you go. 1, 2, 3, 4, 5, right? So it becomes 1, and then 3, 4, basically. Okay, so you add them up, right? So this becomes 7, this becomes 7, and this becomes 8. So we know it's not going to be that. But actually it turns out that if you name them using either one of these, it's the exact same name, stuff like that. So it doesn't. In this case, it doesn't really matter which one you use. Okay, so the final name becomes right. So you look methyl versus propyl. Now, if you use isopropyl, you're still used to propyl, right? Just like di doesn't matter, iso doesn't matter either, right? So with that, so this would be 1, 2 dimethyl, 4, 2 propyl, 2 propyl, cyclopentane. Okay, we have a cyclopentane, right? A carbon 1, carbon 2. We have methyl groups, right? Again, I've got a di here, so I need 2 numbers, right? And then, hey, we have a 2-propyl group. Where is it attached? It's attached to carbon 4. Okay? There we go. Okay, next up, cis and trans, right? So cis, right? So cis, right, equals either both up or both down. Well, trans means up and down, one up, one down. Okay, so for these, so for the cyclopentane, right, it's pretty easy, right? This is up, right? That's up, right? Because a down would look like that, right? Right. So they're both up, so this is cis. Okay. Now for these, it's usually a good idea to go ahead and see where the axial and equatorial go, because the axial and equatorial one's up, one down, right? So like that. So like this, right? So the carbon-carbon bonds point up, so that means the axial's up, because remember they point towards the axial, which is up. That means the equatorial is down, right? Same with this one, right? The carbon-carbon bonds point towards the axial, right? So that means this is up, and that's the equatorial's down, right? So they're both up, so this is cis. Okay. Now this one here, right? Again, the axials point up, right? So there's one up here, right? There's the axial up. That means this is down. Okay. So in this case, right, there's the axials point down, right? Which means the axial's down. This is equatorial, means that's down. That means this is up, right? So we have a down and up, so that means this is trans. Okay. Let's see if I can make this a little clearer. Just give me a second. Let me make sure that this stays clear for you guys. Okay, so there we go. Okay, next up, identifying R and S. Okay, so the first thing we're going to do is have to establish priorities. Right, and that's usually done by molecular mass. Okay, so with that, and then we have to do 1, 2, 3, 4. Right, so with that, so we can either do the steering wheel method or the hand method. Okay, so here we go. So there's actually going to be an arrow, right, for all of these to tell you where it is. But in this case, I only remember to do it on that one. So like that. But okay, so like that. So here we go. So for this one, here, right. So you look exactly what's attached directly to this carbon atom where I'm pointing, right. So with that. So we have a chlorine, a hydrogen, a carbon, and a carbon. Okay, right. So just from mass terms, the chlorine's the heaviest, right. So that's going to be a number 1. The hydrogen is right. Then the carbons, but we don't know which one at this point. Okay, so that's going to be 2 or 3, and then we know the hydrogen is going to be 4. Okay, and so we do, remember, so we look at that carbon and we say, okay, right, this one has 2 carbon-carbon bonds, right? It has 2, and actually the 2 that aren't shown is 2 carbon hydrogens, right? This one here, right, so that's 3 carbon-carbon bonds, right? So 1, 2, 3. That means that there's 1 unseen carbon-hydrogen bond, right? So we compare the heaviest things that are hanging off of it, right? So this has 3 carbons, 3 carbon-carbon bonds. This one has 2, right? So this side is going to be side 2. That side is going to be side 3, right? So you want to rewrite it like this: 3, 4, or 3, 2. Okay, so it's going around like this. It's easy with the steering wheel method, right? Because you need, with the steering wheel method, 4 has to be going away. It has to be on a dash. Okay, so it's clockwise, right? So that would make this R, right? But if you want to do the hand method, right? So your thumb points where the 4 is, and then your hand sweeps from 1, 2, 3. Okay, 1, 2, 3. Your fingertips will sweep from 1 to 2 to 3, with your thumb pointing to where the 4 is. Okay. So like that. So it's an R. Since with the hand method, since you're rotating with since it rotates naturally with your right hand, it's R. So like that. So, okay, so this one here, right? So we're looking at that carbon there. So we have a hydrogen, a carbon, carbon, carbon. Okay, so for this one, right, so the carbons are definitely heavier than hydrogen, right? So this one has to be 4. Okay, but now these are all, we don't know about these guys here. So this one, right, so this one has 1 carbon-carbon bond, right? 2 carbon hydrogens that aren't shown, right? Because two bonds are shown, that means we have 2 hydrogens on here, and 1 carbon chlorine, right there. This one here, right, has 2 carbon-carbon, right? 2 carbon hydrogens, right, that aren't shown. Same with this one, 2 carbon-carbon, right? That means that there's 2 carbon hydrogens that aren't shown, okay? And notice that we have carbon-chlorine versus carbon-carbon, right? So this is going to be the higher priority because it has the heaviest thing hanging off of it, okay? So this is actually going to be number 1, okay? But these two are tied, okay? So when that happens, right, so then we go out 1 atom further, right? So here, again, we have, you see 2 carbon-carbon bonds, right? So that means that there's 2 unseen carbon hydrogens. This one here, right? There's 1 carbon-carbon bond, so that means that there's three carbon-hydrogen bonds that are unshown, right? So for here, we're going to look at 2 carbon-carbon versus 1 carbon-carbon. So that means this side, right? This side is 2, this side is 3, right? So here we go. 3, 4. 1, 2. So if you, right, so it's rotating this way, right? Okay, so with the hand method, right, your thumb would be pointing out, right, because it wants to go with the 4, and it sweeps 1, 2, and then around. Oh, don't break my wrist. 3, right? So since we're rotating with our right hand, right, so this would again be R. Okay, now it looks, oh my goodness, the steering wheel method would say that it's going counterclockwise, which would be S. But remember, the steering wheel, the 4 has to be behind, right? Now here it's coming out at you, right? So if you're going to rotate the molecule, rotate these 2 switch sides and then these 2 switch sides, so it ends up looking like this. Oops. Right, so you take your model kit and just rotate the thing. These 2 are switched, these 2 are switched. So it's 1, 2. Okay, and so it ends up looking like this. 4 behind, which again, clockwise, which again says R. Not so bad. Okay. Now this one here. Okay. So, right, we have hydrogen, fluorine, bromine, carbon hanging off of this carbon here. Right. So, what's the heaviest? Right, the bromine. So that's being number 1. The next heaviest is this one, the fluorine. This one here is, right, carbon is 3, and then hydrogen will be 4. Right. So. 1, 3, 4. Right. So if you want to do the, right, so it sort of looks like, sort of rotates like that, Okay, so the hand method, right, your thumb would point where the 4 is, which is here. The 1 would be behind, the 2 would be up, come out at you, and then the 3 would be over here, right? So it sweeps like this. Since you're sweeping with your left hand, right, it would be S. Okay. Now, if you want to do steering wheel method, you're going to have to rotate this 4 behind, which shifts this up here, right? Shifts the 3 up and puts the 4 behind. And in doing that, that shifts the 2 over here and the 1 over here. Okay, which like that. Get your model kit out. I don't have my model kit out, but get your model kit out and take a look at those shifts if you're doing the steering wheel method. Right, it's going like this, which again is S. Okay, not so bad. So there you go. RRS. Okay, next up, draw the reaction diagram. Okay, so there's a couple things, right? So one, I'll actually show you this on the test. I forgot to include this on here. So it'll say like A to B. Like if I were to do this, it would say A to B to C to D. Okay, so there's 2 very important things you have to look at. One is, where's the slow step? And they said second step of the reaction is slower than the first and the third. Okay, so this is the first, second, third. So this right here is the slow step. Okay. The other thing you have to do, so slower, right, or faster or whatever. Okay, the overall reaction is also not spontaneous. So not spontaneous. So we're looking at that as well. Okay, so here we go. So we have our coordinate here, right? So energy, it would be energy and then reaction progress. Right? So you just arbitrarily say where the reactant is. So reactant. Okay? Right? So all the delta G's are going to be relative to that, to where A is. Okay? The intermediates, which are here to here, right, are going to be above. You just put them at the same level, who cares? Right? But where do we put the product, right? So this is B, C, right? These are intermediates. Okay. Where we put D is depending on where the spontaneous. Spontaneous means that it's actually non-spontaneous, means it's actually above this one here, right? So it'd be up here. If it was spontaneous, it would be down here. But here, it's not spontaneous, so product. D. Right? So because it's this gap here that is delta G0. It's that right there. So that goes there. Relative to spontaneous, it's non-spontaneous. Non-spontaneous, it's above this line. If it's spontaneous, it's below. Okay? The other thing, the other delta G, again, is relative to this, but it has to do somewhere up here. Who cares? It's all relative. Okay, so this is going to be delta G0, or delta G double dagger. Okay? Now, the question becomes, right, so we have transition states, but one of them is going to touch that. Okay? The one that touches is going to be the slow, whichever you figure out the slow. So the slow one is going to be the one that touches up here. Otherwise, everything else just goes, basically doesn't touch it. Okay, so this one here is the slow step, so this is the one that touches that top upper line. Right? So these are transition states. Here, here, and here. These are the intermediates, right? Product, reactant, delta G0, right? It's above the reactant, right? It's because it's not spontaneous, right? This one here is relative, the overall delta G double dagger, right? Is where the slow is. Okay, delta G double dagger. There you go. Not so bad. Okay, naming alkenes and alkynes. Okay, so when naming alkenes and alkynes, you're gonna have to tell me cis or trans. Okay, so here's an alkene, right? So always good to look the where the hydrogens are. Okay, but when don't forget, put in your dots. Okay, again, do your main chain, right? So it has to include this double bond, right? So okay, so here you go. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, well, so it's not really going to matter, but we'll take the horizontal just out of tradition. Okay, so it's 6, so it'll be hex. So right, C6, right? Normally hexane, right? But we have a double bond, so it's a hexene. Right? Don't forget they go CC, ane, C double bond C, ene, C triple bond C, yne. They're done alphabetically. Oop, I can say single A, E. It used to be I, but they transitioned to a Y, 100 years ago or something like that. But they were intentionally written like this. For a single, double, triple, they go alphabetically, stuff like that. So okay. How about that? So what do we need? Okay, we are going to need to know where that alkene starts, right? So we put this in parentheses. Okay, and then we also have that one there, side chain, ethyl. Okay, so now where do we start the numbering? We start at at the site closest to the double bond. Now that the double bond gets priority here, so it's definitely going to be 1, 2, 3, 4, 5, 6, right? So it starts at carbon 2. This one's attached to 4, right? So it's going to be 4 ethyl, right? 2 hexene, right? So we have a main chain, right? Hey, with the double bond in it, where's the double bond starts? Carbon 2. We also have an ethyl hanging off of carbon 4. Now, is that ene, is it cis or trans? Well, notice how these hydrogens are on the same side, so that makes it cis. So it's actually cis 4-ethyl 2-hexene. Not too bad. Okay, now for this one here, right? Put in your dots. Okay, so here we go. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Right? So here we go. So here's our main chain. Just so happens to be the main one, or the horizontal one, right? So it's C8, right? Which would normally be octane. But since it's a triple bond, it's octane. Okay, so we're going to need to know where the alkyne is. Right? But we also have this side chain, right? Right, so it's 1, 2, 3, right? So it's propyl. But since it's connecting through carbon 2, it's a 2-propyl. We also have this one here, which is a methyl. Again, like the double bond, the triple bond, the numbering needs to start at the side closest to the triple bond, right? So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, right? So the alkyne starts at 1, the methyl's at 4, the 2-propyls at 5, right? So it becomes, right? So which comes first, propyl or methyl? Now, again, methyl. Now, if it's isopropyl, this would also be named as an isopropyl. Again, it's just the propyl that makes the difference, right? So it becomes 4-methyl, 5 2-propyl, right? So we have a 2-propyl group attached to carbon 5. Right? 1 octyne, right? We have a main chain that's 8. We have a triple bond in it. Hey, where does the triple bond start? It starts at carbon 1, goes from 1 to 2. We also have a 2-propyl group, right? Where is it attached? It's attached to carbon 4, or carbon 5, excuse me. Okay, we also have a methyl group, right? Where is it attached? Carbon 4. There you go. Not too bad. Okay, E and Z. Okay, so these Prelog rules, these are the same rules that we used for the for R and S. Okay, so if you remember, E is opposite, and Z is same. Right? In your worst German accent, you could say on the same side, right? Something like that. So I apologize to my German grandparents. Something like that for that. Something like that bad accent. Something like that. So, but right. So we're looking at the high. We're going to have a high and a low priority on each side of the double bond. Okay, something like that. So if the high priorities are on the opposite side, it's considered E. If they're on the same side, it's considered Z. And we're going to do the high and low over on this side, the high and low on this side, and we'll take a look away, or take our hand away, and then look to see where the highs and lows are. Okay, so there we go. Okay, so on this side, we're going to just do this side here, right? So we have chlorine versus nitrogen, right? Chlorine's heavier than nitrogen, right? So this becomes high, this becomes low, right? And then here, right? So we have, right? So we have carbon, carbon, right? So this has 2 carbon-carbon bonds, 2 carbon hydrogens, right? Same as this one, 2 carbon-carbon, 2 carbon hydrogens, right? There's a tie here, so we go one out, one carbon further out, 1 atom further out, right? So here, right, we have this carbon has 2 carbon-carbon bonds, right? This has 2 carbon hydrogens, right? Which you don't see, which don't need to be written. This one only has 1 carbon-carbon versus 3 carbon hydrogen, right? So 1 versus 2, right? So that means this is high, this is low, right? Since the highs are on the same side, that makes this a Z. Okay? So for here, right, so we have hydrogen versus carbon, right? So this is going to be low, this is going to be high. Again, we have this here, right? So we have carbon-carbon, right? So this is, right? So it's 2 carbon-carbon versus 2 carbon-hydrogen, right? This one only has 1 carbon-carbon versus 3 carbon-hydrogen, right? So it's 1 versus 2, right? So like that. So this is the high, this is the low, right? So high, high on opposite side. So this is E. Notice that we didn't even have to worry about this chlorine over here. You know, we just start working our way out, 1 atom at a time, right? So as soon as we see a difference, we can stop. Okay, so like that. So we had hot, right? So we had high, high. It had nothing to do with any of these, really any of these guys out here. Okay, there was a difference at that first carbon, and so we stopped. So high at the top, high at the bottom. So this becomes E. Oops, sorry, forgot to move that. So there we go. Okay, so these are going to be the 2 types of reactions. It's going to be this, I believe they were on exam 3, stuff like that. So it's the same ones, they're very similar ones, right? So like that. So I'm going to give you something like this. And actually, I'm going to give you the product, right? So it's going to look like this. So that's what it's going to look like. It's going to say, draw the mechanism, right? You have to include, right? You're going to have to include the formal charge, and it'll say that in the directions, and any resonance structures. Okay, so here we go. So if you can see, think of this bromine, right, as BR, right? We're going to have this double bond attack and go here, right? Which makes, right? So don't forget there's a hydrogen here, so there's a hydrogen there, right? So now this goes from having 4 bonds to only having 3, so there's a positive charge there. So Br minus. Now there's a resonance structure, right? Because we have this set of lone pairs, right next to a positive charge, right? So this is going to attack there to give this resonance structure. Right? So that set of lone pairs becomes this new bond. Okay? So this is bouncing back and forth, right? So with that, so this negative charge is then going to attack the plus charge, right, to give that. Now, the only difference is that if I had water down here, right, the only difference is, 1, the products can be a little different, OH versus Br, but these steps here on this side are going to be the exact same. The only difference now is that the water comes in and attacks instead of the bromine to give that. Okay, that's the only difference. But these 3 steps are the exact same, whether or not it's chlorine or bromine, or whether or not you have water or not. Okay, it's just what attacks at the end. Is it going to be the water, or is it going to be the bromide or chloride that got kicked off here? You know, gets kicked off there. Okay, stuff like that. So that's the only difference between the mechanisms. Okay. There you go. Now. Now, the reactions. Okay, so we're gonna walk through these reactions. Okay, because they're sort of grouped. Okay, so like that. I tried to group them at least a little bit. Okay, so these 2 here. Those are grouped together in basically how you make a double bond. Okay, and so what's happening is there's a hydrogen on either side of where either the OH or the Cl is leaving. Okay, and essentially what happens is these 2 go away, and the scar that remains is the double bond in between there, right? So if it attacks, if it grabs this, so if this comes in and grabs that hydrogen, that falls down, kicks this away. Okay, so like that. So, but essentially what happening is that if that hydrogen gets grabbed and that thing goes away, the scar between those 2 carbons where those things were attached becomes a double bond. Or it could do the same thing on this, or it could do it on this side because there's a hydrogen there, to make these products. But this is how you make a double bond. One of the ways that we're talking about. So, okay. Now these guys here are also the very similar, right? They all have the exact same mechanism, right? So they're all going to be this attacks that and then kicks this away, right? This attacks that, kicks that away. This attacks that, this kicks it away, right? What ends up happening is this thing on the left here gets added first, right? So this is and it always seems to go on the lower numbered side, right? So it always gets, right? So this is secondary versus tertiary. It gets added here, right? So H, X, X. Okay? Now, and then, right, because you're going to form a carbocation intermediate, right? Stuff like that. So you always end up forming, right, this right intermediate. So the carbocation is going to go in here. So what's over here, so what then comes back and attack, it's either this X, those two come back and attack on the higher numbered side, right? Or in this case, the wet solvent, right, we have water in there, that comes in and attacks to add on the higher numbered side, right? So that these are all exactly the same thing because they use the same mechanism. Okay. Now, these guys here, right? So these two are complementary to each other. These add, right? So these add OHs, add OH groups onto, add OH groups onto where there were double bonds. Okay. So, but they're complementary, right? Because this is tertiary, right? This is secondary. This one here adds to the higher numbered side, so tertiary. This one adds to the lower numbered side, right? So if you had so this one again, tertiary, secondary, right? So here it added to the tertiary, added OH on the tertiary side. Here it added to the secondary side. Okay. Now if you had primary versus secondary, right? This one would add to the secondary, this one would add to the primary. This goes on the higher number, this goes on the lower number, right? So we're using our toolkit to do it either way. Okay. This one here, right? If you have a double bond in the presence of just hydrogenation, palladium, just straight hydrogenation, just takes out the double bond. That's all it does. Okay, it adds hydrogens across here, so it just takes out that double bond. Pretty easy. You're hydrogenating it. Okay. Okay, now for this one here, what's happening is MCPBA, right? It makes this epoxide, it makes the triangle. It makes the triangle with the oxygen in it, right where that double bond is, right where that double bond is that's where it goes, right? So like that. So that's one you just kind of have to know. Okay, but if you add this to if you then react it, if you react it with with alcohol, you actually get the cis triple. Here you go.
Sorry to interrupt.
Okay.
I'll bring it back.
So the epoxide is actually made. So the epoxide is actually made on the on one side. Okay. So let's say it's like this. Okay. If you were to react it with the acid, this comes in and attacks from the back side. Okay. So you would end up with the trans alcohol. Like that. Okay. So if you want to make the trans alcohol, that's how you do it. You do these two steps. Okay. If you want to make the cis alcohol, you can do it in one step using osmium. Osmium adds right onto one side. So if you wanted to make the cis version, right? So this is trans. If you want to make the trans alcohol, or excuse me, the cis alcohol, you would use this osmium one. Okay. So these are actually related. Actually, these two are related. Okay, for making the trans versus the cis. Just like this one over here, right, was making the higher, putting alcohol in the higher or the lower, right? This is the difference between making trans and cis. Okay. Okay, now ozone and permanganate, again, actually these are related as well in slicing carbon bonds. Okay, what you do here is you actually slice between that double bond and you add an oxygen on either side. Stuff like that. So, okay, stuff like that. So, in this case, right? So, carbon piece, right? Double bond to O. Okay, carbon on one side, methyl on one side, hydrogen on the other, double bond O. Okay, no problem. Now, this actually is what this does as well. However, this aldehyde group can't survive. Okay, so it actually turns this OH, the H group here is coming right, the aldehyde, so it's the H coming off the C double bond O, turns it into an OH. So there you go. So it makes it into carboxylic acid. The ketone is resistant to it, but the aldehyde doesn't survive. So like that. So these are interrelated, right? So you slice oxygen there and there. Okay. Now, this one here also slices, but what it does, right? So don't forget there's a hydrogen here. Okay. So if you have OHs on the same side, right? So this one, it would slice on this molecule, right? It's slice right there. It's, again, slices between the carbons that have OHs on them, okay, and permanganate, and turns them into C double bond. Where are the oxygens where it turns into C double bond, right? So methyl on either side. Here, methyl, hydrogen, right there. So it's another way of slicing. Like that. So, and then these two are grouped together, and that they both make the cyclopentane, right? But this one, right? So this carbon here becomes that carbon there. That carbon there becomes that carbon there, right? It's going to add right to where that is, right? So that those carbons, right? Don't think those are oxygens; those are carbons, stuff like that. But when you do it under this conditions, you add chlorines on it. When you add this conditions, you just make without the chlorines, there's hydrogens there. Okay, but again, you make the cyclopropane using this one. This one here puts the chlorines on. This one just leaves the hydrogens away. Okay. For the alkynes, okay, so this is how you make an alkyne, right? It's actually what you're doing is you're actually doing this twice. You're just doing the same thing that you did before to make a double bond. You're just doing it twice, right? But now, right? So there's a hydrogen here, right? So that plus KOH gives you a double bond, right? You just do it twice, and you make a triple bond. Okay, this one again, it's one of those where you add, you're going to add, this adds here, right? This adds there, right? So like that. So this goes there and there. So this adds first to the lower numbered side, right? So lower number, and this adds to the higher number. Okay, so like that. So it doesn't show it here, right? But the H is going to, because you make a carbocation, and then, that needs to go on the higher side, right? That needs to go in the tertiary versus the secondary, things like that, which then comes back. Okay. Again, these guys here, again, are interrelated. Okay. This one, like the mercury is going to go on the higher numbered side. And the BH3 is going to go on the lower numbered side. Lower. Okay, now, for triple bonds, internal triple bonds, it doesn't matter, right? Because it's secondary versus secondary, right? You can't have anything else hanging off of it, right? So you're actually going to get a mix of the two, right? So it really doesn't matter between which one, right? So that's secondary versus secondary. So half time is going to go here, the other half time is going to go there. Same thing with the BH3. Half time is going to go there, the other half is going to go there. Now, on terminal alkynes, right? Now, right, because these guys are all secondary, right? So there's no difference. But here, you have secondary versus primary. Now you're getting, now you can get a difference, right? So now this is going to put an OH there versus there. Okay, the BH3 is going to go there. Now, I forgot to mention, right, so that when you formed this, right, normally you would do a second time. That rearranges itself, right, wherever that OH goes, it snaps into becoming where the C double bond, the double bond and the CO bond basically switch, sort of thing like that, right? Stuff like that. So wherever the OH goes, it snaps around to make the C double bond O. Okay, so it's going to go here, right? So here, this is the lower number side. That's where the OH initially went on there, and then it snapped around and put it there. This is the higher number side, which is where this one wants to go. We originally put the OH here, but it snaps around to make it, to put it there on the secondary versus the primary. Okay, but it's the same concept as the other ones. Okay, this one here, if you just do, so these again interrelated, right? So if you just have regular hydrogenation conditions, the triple bond is going to get taken down to a double bond. There's no way for it to stop after the first addition down to the double bond. It's going to be too reactive to go down. So what you do is, in order for it to stop it at just a double bond, you have to poison the catalyst. Okay, and that's what the Lindlar is. It's a poisoned catalyst. It's not. It just simply doesn't have enough oomph to make it go down to the triple bond or down to the single bond here. Okay, but since the hydrogens are getting added on one face, right? Because remember this is the palladium surface, right? The hydrogens are sticking up, and the molecule has to sort of come down onto it and picks it up on the same side, right? So they end up adding on the same side. So this is the cis version. Okay, to get the trans version, you actually have to change the chemistry quite a bit into this, the lithium ammonia, and that gives you a trans addition, right? Right, this is up, right? This is up, down. So if I want to go from triple bond to a cis double bond, you need to do H2 Lindlar. If I want to go from a triple bond to a trans double bond, you need to do lithium and ammonia. Okay. Now again, these two, these guys here, are exactly the same as what we were doing before, where you slice, right? You slice here, and then you put oxygens on here. Now here you've got three, right? You would make 3 carbon oxygen bonds, right? So here they are, 1, 2, and 3, right? 1, 2, 3, right? So about that, oxygens on either side, right? So this one, they both make carboxylic acid. Now the quirky thing is that if you end up getting, if it's a terminal, this carbon here ends up becoming, it does become formic acid, but that gets further oxidized to CO2 and water. That breaks down to CO2 and water. Okay, so really you just have the one product. If it's a terminal, you just have one carbon shorter carboxylic acid. Okay, here you, stuff like that, but it's the same mechanism. Now this one here, this is the way that you guys were taught for exam 3, how to make carbon-carbon bonds, right? So this thing here is a very strong base, so it's going to grab that hydrogen and move those electrons onto there to make this. This is a really good nucleophile, and then you got to pick, right? So your bromide comes in there, attacks there, and now you've attached this piece here onto the end. You've extended out your chain, okay, like that. So this is how we initially learned how to make carbon-carbon bonds. You take that triple bond, you know, rip off the terminal hydrogen, and then react it to alkyl bromide to make it extend out that chain. Now, the chapter 10 reaction showed some different, some new ways to make carbon-carbon bonds. Okay, so first off, we're going to talk about adding bromines on, adding halides, right? Stuff like that. So here, what you're looking for is CH bonds on alkanes. Okay, so if it's on any sort of double bond, the carbon can't react, right? So these are all single bonds, right? Right. So we can add it here. You know, we can add bromines to all of these, right? So if it adds there, it goes there. If it adds here, you make that one. It adds here, it adds here. Now, this one here, right? It will add there, but that molecule is just this. Okay, it's just that, just flipped. Okay, same goes with this one, right? Put a bromine there, it's just, right? Put a bromine there, it's just this one flipped. So really, there's just three different types of molecules there. Okay, this one here, it's looking for allylic. Okay, which is one away from the double bond, so it's here and here. Okay, so you can add a bromine there, which is this one. You can add it there, which is that one. Okay, on either side of the double bond. Okay, like that. So, Okay, this one here, this really only works with triple bonds, somewhat with double bonds, or tertiary alcohols, sort of with secondary. Definitely does not work with primaries. Okay, but all you're doing is you're swapping out this Cl for this OH. Okay, so this was originally how they did it. On that. So really, these are all how you swap out alcohols for halides, right? So this would work the same as, if it was HBr, right, you would put Br there. If it was HI, you would put I there. So, but this one is very more specific, more general. This will work pretty much just with tertiaries. This will work with primary, secondary, tertiary. It doesn't really matter, right? So this goes to Cl, so Cl2, so thionyl chloride. This one puts on bromines, right? So bromines. This one puts on fluorines. Wherever those were, they get transformed into their respective halides that you had, right? So that, or that. Okay. Okay. Now these guys here, right? So, okay. Again, they're related. Okay. So here you insert a metal where the magnesium bromide bond is. Okay, so this one here is a -1, right? So magnesium is traditionally +2, right? So it needs an extra -1, which is why the bromine sticks around. Here, at this position, right, that is -1. Lithium really only needs +1, right? So we can get rid of the bromine. We don't need it. Okay, so that's why you have the bromine here but not lithium there. Okay. It's actually also why it's here, right? So this is -1, this is -1, these two carbons here. Copper is going to be like a +1. Okay, lithium, right? So minus, minus, plus. So we're going to need that lithium around for a +1. It's a little more complicated than that, but you can sort of think of it like that. Okay, so that's how you prepare it. You literally just chuck in magnesium ribbon or lithium metal into your bromide and it swaps it out. Okay, now all of these work by wherever that metal is attached, you make a new bond where the halide is there. Okay, and actually it works the same as this one too, right? Where this boronic acid is, that attaches right where the halide is on the other side. Okay, so that's where it goes. Here, right? So here's the new bond that's made. Here's the new bond that's made. Right? These two carbons here are just these two carbons there. Okay, here's the new bond that's made, right? So this should actually get, if you want to, right? So you get for your rotation, right? So like that. So that's the new bond that's made. This is where the boronic acid was. This is where the boron was. This is where the boron was. This is where the copper was attached. Bromine, lithium. Magnesium bromide, bromide. Oh, I'm sorry. Lithium, bromide, copper, boronic acid, boron, or bromine, stuff like that. So they all work exactly the same way to make new carbon-carbon bonds. Stuff like that. So, all right. That's okay. Multi-step synthesis. This is the bane of everyone's. All right. So I'm sorry, copper. Forgot to move that. Okay, multi-step synthesis. Okay, so usually what you're going to want to do, okay, is to, so for this one, there's actually a couple of different ways that you can do it, okay? But typically, right, so what you'd want to do is to go in and figure out what the, how you put in the functional group that pops up, okay? And so how would you do this? How would you put in a ketone, right? So like that. So what you do is you say, okay, irrespective of anything that happened before, right, is to say, okay, the way we probably want to do this is to make a triple bond and go in like this, right? And I'm from Purdue, so I prefer hydroboration. But you could also do the magnesium acetate, okay, and that'd be fine. right? Because make a triple bond into here, and it doesn't matter, right? Secondary versus secondary, so you're going to make this. And actually, because this molecule is symmetrical, if you put the OH here, right, you make that molecule. If you put the OH here, which then snaps around to the C double bond O, because it's a triple bond, right, it's actually this molecule just flipped, okay? So it doesn't really matter, actually, which way you do it. So really what we want to do is we really want to build this molecule. Okay, so you do this last step, and then you take these components to try to build this. Okay, and so you can sort of think about this as this here is probably going to be that. Okay, and then all we really need to do is add a 2-carbon piece on either side, right? Which would be this one here. Okay, and so what we really need to do is we need to start with that. Okay, add the sodium amide. You have to go through this this process twice to add it on one side, right? And we're going to add a 2-carbon piece, right? Add this 2-carbon piece here, right? Now, we're going to go through that same process again. Now we're going to take off that hydrogen. We're going to react again with that 2-carbon piece. Right, so now we've got a 2-carbon piece on this side going to a carbon triple bond, and 2-carbon piece on this side. So when we hit it with, in this boron and peroxide, there we go. That is that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? So you take the molecule, you flip it, it looks like that. Okay, but we need to know what that last step is, and so that we know what the carbon pieces we need to get to look like to do that last step. Okay, so do this, and then start building up to that, and then do your last step. Okay, next one here, right? So again, right? So how do we make a, right? So you can put in the hydrogen a little easier to see, okay? So how do we make a cis, right? How do we make a cis double bond? Right? We need to start with, the triple bond and hit it with H2 Lindlar. Okay, so it's going to need to look like, right, so 1, 2, 3, 4, right, 1, 2, 3, 4 with a triple bond, right, where that double bond is, that's when to start with a triple bond of methyl groups on either side. Now we could start with this one here and put a methyl group on either side, or we could just start with this one, right, we could just start with that, right, and add a carbon group onto it, a single carbon group on that. So I think it's easier to do that, although either one's technically correct. Right, so we're going to start with this. Hit it with sodium amide. And our CH3Br, right? So that text there. To make that, right? Our 4-carbon, right? 1, 2, 3, 4, 4-carbon piece. H2 Lindlar. There we go. No problem. Stuff like that, so not too bad. Okay. Last couple pieces of exam 4, right? So with that, so people did pretty well in this exam, so hopefully this will be a quick review. Too much of a review, I should say. So okay, so here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Okay, so for this one here, right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, right, or you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, right, so don't forget to go down the side chains, right, so we'll go down the side chain just to have fun, right, so it's going to give the same name, right, as long as it's the longest chain, okay. Okay, so what side chains do we have? We have this one here. We have an ethyl, right? Well, we have the bromo, right? It's a bromine, so it becomes bromo, and then that methyl group there, methyl. Okay, so now remember, the bromines have the same, they don't give priority for sides, right? So it's just like a methyl group, right? So we're just gonna have to go from one side or the other, right? So here we go. So we're gonna take this 1, 2, 3, 4, 5, right? 6, 7, 8, 9. So you see the ethyl group, which is here, at 3. The bromo's at 5, and the methyl's at 6. Okay, the other option would be to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so the methyl's at 4, the bromo's at 5, and the ethyl's at 7. Okay, so this is 9, that's 14. This is 9 and 7, so it's 16. So we're going to take these numbers here. Okay, so which comes first, ethyl, bromo, or methyl? So bromo comes first, it becomes 5 bromo. Oops, I forgot to do the, right, C9, right, it says octane. Oh, octane. Nonane. I think I did that in class too. C9 is nonane, right, so like that. So I'm sorry. Get back here, so 5 bromo. Right, which comes next, ethyl or methyl? Ethyl comes next. 3 ethyl. Okay. 6 methyl. Right? Nonane. Too bad. Okay. Okay, so here we go on this one. Here, right one. Okay, so we either have to do straight chain or we have to do cycle, right? So with that, so ring, right? So here's our ring, 6-membered ring, right? The longest straight chain is this guy here, right? So it's only 3 long, right? So here we go. So C6, right? Hexane, right? But since it's a ring, right? So it becomes cyclohexane, right? So again, we have a chloro, right? We have this methyl, right? And then again we have a propyl, but since it's connected through carbon 2, it's a 2-propyl. Okay? So here we go. We're going to set each one of these to 1 and see where it gets us. Okay, so if this is 1, it's 1, 2, 3, 4, 5, 6, right? So the propyl is 1, 2, 3, and then that becomes 4. Now, if we set this at 1, remember we go towards our nearest neighbor, so 1, 2, 3, 4, 5, 6, right? So this becomes 1, 2, 5, right? Or we can set this at 1, so 1, and we go towards the nearest neighbor, so we have to go back this way, 2, 3, 4, 5, 6, right? So 1, 2, 4, right? So add them up, right? So this becomes 8. This becomes 8, this becomes 7. So this is the numbering we want. Okay, which comes first, methyl, or propyl. Again, if it's isopropyl, you still just go propyl, right? So it becomes 1 chloro. Methyl comes before propyl, so 2 methyl. Right, 4, 2 propyl, right? We have a 2-propyl group at carbon 4. Cyclohexane. There we go. Okay, so these guys here, now I'm actually not going to show you this part here. I'm going to show you the trios, tetras, petras, whatever. I'm not going to show you this top part here. Okay. So what do you have to do, right? So, well, there's 2 things, right? So we need to say, is it a carbon or an aldehyde, right? So, or a ketone or an aldehyde. So ketone, right? Because there's carbons on the other side, right? So that makes it a keto. This one here, it's an aldehyde, right? Because you see there's a hydrogen on here, so this would be an aldo, because it's an aldehyde. And you got to count the carbons, right? 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7. Right, we don't stop it here, right? Don't forget there is one carbon here, but don't stop when you get there, right? Do this one as well. 1, 2, 3, 4, 5, 6, 7. So come down here, 7. So heptose. So it's a ketoheptose. Okay. This one here, and 1, 2, 3, 4, 5, 6. Don't forget there's a carbon here. Don't count the hydrogen, right? Because it's hydrogen. We're only counting carbons, right? 1, 2, 3, 4, 5, 6. Right, so like that's 6, right? So that'd be 6 is hexose, so it's an aldohexose. There you go. Okay, so for D and L, right? So for straight chain, right? All we need to look at is this one here, the chiral center farthest away from the C double bond O. Okay, and so if it's pointed this way, right, like this is, it's a D. If it's pointed this way, it's an L. Okay, for cyclic forms, you look for this CH2 group. Okay, if it's above the chain, like this is, it's D. If it was pointed below, so if it was down like this would be, if it was below, it would be L. That's all you gotta look at. Nothing else matters. Okay? So there we go. Last up, linkages. So like that. So okay, so you have to remember, right? We're going from left to right. Okay, so when you do this, right? So we'll get the numberings first, right? Do this in blue because it's in black ink, right? So if this is a 6-membered ring here, right, that means it's a 6-carbon sugar, right? So the one outside is going to be the last carbon, so this would be 6, 5, 4, 3, 2, 1. Okay, for here, again, your carbons, don't forget there's a carbon there and a carbon there, right? There's a kink, right? So 6-membered ring, so carbon 6 is going to be out, so 6, 5, 4, 3, 2, 1. For here, right, there's a kink here, so there's a carbon. Right, so 6, 5, 4, 3, 2, 1. Right, here we go. Six, 5, 4, 3, 2, 1. Okay, so now we're looking at this linkage here, right? So right now all we care about, right, is the left and the right-hand sugar, right? And where is that linkage, right? So alpha, right? Remember alpha is going down, beta is going up, right? So here we go. So this is the left-hand sugar for this linkage, right? So this is going, right? So this is going down, right? So that means alpha, and it's going from left to right, so it's an alpha going from carbon 1 to carbon 6. Okay, for this one here, right? We only care about these two. This is left, this is right. Okay, this one's going up, right? So like that. So you can actually just cover that up, right? So that's going up. So that's going to be beta. Right, it's going from carbon 1 to carbon 4. Okay, now for this linkage here, right, we only care about those two sugars. Right, so here's the left, right? Notice how the ring is slid slightly left compared to this one, so that means this is the left-hand sugar. Right, so that linkage, right, that linkage is going down relative to the left-hand sugar. Right, so it's down, so it's alpha. It's going from carbon 2 to carbon 6. So it's an alpha 2,6. Not too bad. Okay, good luck. Stuff like that. And let me know if you have any questions.